Hey y'all. Today we're going to look at the next way that atoms can differ, and that's in their masses. In today's video, we're going to start by talking about what is an isotope. I'm going to give you the definition, I'm going to give you some examples. Then we're going to talk about how we actually will see the impact of different isotopes when it comes to determining the mass of atoms and the numbers that we actually see on the periodic table. Next, we're going to look at a mass spectrometer. This is a device that we actually use to predict the fractions of different isotopes in a sample. And we're going to look at the relative abundance of different isotopes of different elements and talk about something called a weighted average. We're also going to be able to, by the end of this video, predict the frequency of different isotopes, knowing what their average atomic mass is. So let's go ahead and get started on this. Starting with a basic definition of an isotope. By definition, each atom of the same element has the same number of protons. However, they can vary in the number of neutrons that they have. So maybe my two atoms here have the same number of protons, but a different number of neutrons. This leads to a different mass. They are different isotopes. The mass number of an atom is its mass of protons and neutrons combined, added together. When we look at mass numbers, we measure them using the unit AMU, atomic mass units, and they are whole numbers. Now, when we're looking at a mass number, we're going to go ahead and assume that both protons and neutrons weigh exactly 1. That's going to make the math a little bit easier, and although it's not exactly true, we're going to be able to use that today and this year in AP chemistry as a standard assumption. One thing to be aware of is there is a difference between a mass number and the number that you see on the periodic table as the atomic weight. The weight that you see on the periodic table is the average atomic mass. We're going to talk about that in a few minutes, but understand that the mass number and the average atomic mass are often different. The next thing we're going to talk about is the actual notation with which we use to write different isotope values. So take an example here of carbon. Each carbon atom has 6 protons. So the number at the bottom left of this carbon symbol, C, is a 6. That's the same across all 3. However, where these carbon atoms differ is in their mass number. The first one is carbon 12. Next one's carbon 13. Last one's carbon 14. Now, if they all have the same number of protons, then we can calculate very quickly how many neutrons they have. Carbon 12, with 6 protons, must also have 6 neutrons to give it a total mass of 12. That 12 is going to go in the top corner there, the top left corner, and that's going to tell us the mass of that carbon atom. That specific carbon atom has a mass number of 12, 6 protons, 6 neutrons. Carbon 13 would have 7 neutrons, same 6 protons, but now to make a mass of 13, you'd need 7 neutrons to get there. In carbon 14, you would need 8 neutrons. So you can see both the notation, but also a little bit of the math involved in figuring out how many protons and neutrons are involved in a different isotope to get the different mass numbers. Now, there's a difference between mass number and average mass. Think about it this way. If I had 10 people in the room, 8 of them were 6 feet tall, 2 of them were 5 feet tall. All of a sudden, I can look at a single individual and say, I know what your height is. But in order to determine the average, I couldn't just look at one person. I have to look at all of the people. Same thing with atoms. Average atomic mass is the average mass of all of the atoms of an element. We are going to be able to use these numbers because of the fact that they are provided on the periodic table. The mass that you see, the atomic weight that you see on the periodic table, is the average atomic mass across all atoms of each element. So let's do an example of a weighted average. I like books. We like books. Let's use books. So I've got 8 books that have 500 pages. It's a good read. Takes you a little bit of time to get through. There you go. I've got 2 books with 110 pages. What's the average number of pages across all of my books? Now, the first thing to keep in mind is that we can kind of conceptually understand that we have more books that are big, 500 pages, than we do small that are, 110 pages. Therefore, the average number of pages is going to be greater than just the middle ground between the two. Okay, so it's going to be greater than the average of 500 and 110. This is because it's going to be weighted more heavily towards the 500. The reason it's weighted more heavily towards the 500 is because there's more books with 500 pages. Therefore, it has a greater impact on the average. If you want to think about this in terms of how you actually take an average, what you're essentially doing here is you're taking your 500 pages, multiplying it by the number of books that are 500 pages, 8. Then you're taking the 110 page books and multiplying the 110 pages by the number of books of that length, 2. When we get the weighted average, we're then going to take all of that and divide by the number, the count. But we can do it a little bit differently here too. What we can do is take the number of pages and multiply by the proportion of books that are 500 pages, 8 out of 10, or 0.8. We then add that to the 110 pages times the proportion of books that are, 110 pages, 0.2. So 500 times 0.8 plus 110 times 0.2 gives us an average, a weighted average of 422 pages. So again, logically, we knew that the average was going to be closer to 500 than 110, and the data here shows that. This is how we do a weighted average, and this is how we do it with atoms as well. So when we look at the periodic table, we see the weighted average in the case of the atomic weight. Now, the weighted average is often closest to the most common isotope. So for carbon here, for example, its weighted average is 12.011. The most common isotope of carbon, it's carbon-12. So on average, an atom of carbon is most likely to be carbon-12. And the weighted average results in an average mass of all carbon atoms close to that isotope's mass of 12. So how do scientists even figure out these weighted averages? Well, it's actually not that hard. You just need the right tool to do it, a mass spectrometer. Now, a mass spectrometer is going to take a sample of an element in its gaseous form. It's going to shoot those atoms across a magnetic field. As it does that, the field is going to force those atoms to bend. The atoms that weigh more will bend less. The atoms that weigh less will bend more. And in the end, because these are whole number values, each atom is going to be affected in a different way. So if we can tune this, what we can actually see would be different points at which each isotope strikes our sensor. We then would use our sensor to perceive, we see 3 different strike spots. That means there's 3 different isotopes. One of those strike spots has a power that is 8 times the others. That means that there's 8 times as many isotopes of that than the other 2. So when we look at a mass spec, what we're looking at is data to give us an understanding of how many of the atoms are of each specific isotope. Let's look at a graph that shows me the results of a mass spec run. So here's the example I'm going to use. The mass spec in this case was processing a sample of chlorine atoms. Now, chlorine atoms in this mass spec seemingly have only 2 isotopes. See how there's only 2 peaks, 2 bars? One of those peaks is at a mass of 35. The other is at 37. That means there's 2 isotopes of chlorine, one that weighs 35 AMU and one that weighs 37 AMU. You can see that the height of the mass 35 is greater than the height of the mass 37. This tells me that the weighted average of all chlorine atoms in this large sample is going to be closer to 35 than it is 37. Now, if I look at the relative heights, what I see is that 75% of the atoms that struck the sensor were 35 and 25 were 37. Now I have a number I can use. Using the same equation we used before for the book pages, let's find the mass of average chlorine atoms. What I'm going to do is I'm going to take the 35 and multiply it by 0.75, which is the frequency of all of the atoms that were 35. So 35 times 0.75. Then what I'm going to do is I'm going to take my 37 and multiply it by 0.25. I add those two values together. 35 times 0.75 plus 37 times 0.25, and I get an average mass of these chlorine atoms of 35.5 AMU. So that would be the mass that ends up on the periodic table. And if we look at the periodic table, you can see that the mass of chlorine atoms on the periodic table is shown as 35.45, which is basically 35.5. So it matches the data that we saw in this mass spec run. I want you to do a quick practice problem here. Here I've got the mass spec data from a run of element X. There's no element X on the periodic table, so I'm just going to use this as an example. Element X has 3 isotopes, as you can see from this mass spec run. I want you to tell me what is the average atomic mass of element X. Go ahead and take a few seconds to calculate that and come back when you're done. All right. So did you get an average mass of 20.18 AMU? All right, if you did, great. If not, let's talk about it. And frankly, let's talk about it either way. The way we do this is we take that first mass, 20, and we multiply it by its frequency, 0.9048. We then add that to 21, which we multiply by 0.0027. And then we add that to 22 times 0.0925. When we add all those together and we complete that math, we end up with 20.18. Now, out of curiosity, what element on the periodic table has an average mass of 20.18? Take a look. Did you see it's neon? See, this is one of the ways that we can actually identify atoms on the periodic table just based off of mass spec. I might not know what element is in a sample, but I can use a mass spec to predict which element's in a sample based on what I know about their isotopes, their frequencies, and the average masses. So that wraps up today's video. Let's recap it. Today we learned about what isotopes are and how we can actually use a mass spec device to be able to determine their relative frequencies. We also talked a little bit about how to show isotopes in isotope notation. We also then went ahead and discussed how to do the calculations using mass spec data to determine the average mass of isotopes of a specific element. As we're doing this throughout the year, keep in mind that we can use weighted averages not just for AMU and this data, we can use weighted averages for other things as well. In this case, we're going to use it for isotopes and average mass though. Today's video was written, directed, produced, and edited by Mackenzie Kaiser and Rocco Warrington. I'd like to thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.